In this video, we're going to look at the second part of the chapter where we look at what it means to be an ideal gas, what are the conditions for a gas to behave ideally, and what are the conditions where a gas do not behave ideally. So first and foremost, what does it mean when a gas behaves ideally is that the pressure, volume, number of moles and temperature, they actually obey the ideal gas equation. Okay, notice that when we say that, it means that it does not depend on the identity of the gas, all right, but only the pressure, volume, number of moles and temperature. Okay, so why would different gases behave similarly and be governed by the ideal gas equation? For that, we need to again go back to our knowledge of the microscopic view of gases. Okay, bear in mind that in a gas, the particles are very far apart, all right, so the volume of your particles compared to the volume of the container is very, very much smaller. Therefore, the size of your particles will not affect the volume occupied by the gas. Okay? The next thing is this, that in a gas, the particles are very far apart, the forces of attraction are very, very weak. So therefore, we would assume that the forces of attraction being so weak, they would not affect the pressure exerted by the gas. So having said that, the two very important assumptions or conditions for ideal gas is this, that the particles have no or negligible forces of attraction between them. And two, the volume of particles are negligible compared to the volume of the container. Okay, or at higher levels, we describe them to be point masses. So the particles are like a single point. Now, so having said that, why is it that under room conditions, under ambient conditions, that all gases actually behave ideally? Is this, under ambient conditions, for a gas is considered to have high temperature and low pressure. Okay, so under conditions of high temperature, the particles actually have a lot of kinetic energy, therefore the forces of attraction become very, very negligible. Okay, so regardless of which gas you are looking at, the pressure that they exert will be the same. All right, and also under conditions of low pressure means that the volume is very, very big. Okay, the particles are very, very far apart, therefore the volume of your particles, okay, is very, very small or negligible compared to the volume of the container. Now, having seen the conditions where the gases behave ideally, the reverse of the conditions would mean that the gas will no longer behave ideally. Okay, the gases will no longer obey the ideal gas law. Okay, so the two conditions are as follows. At low temperatures, when the temperatures are very low, the particles have low kinetic energy, they are moving very, very slowly. So when they are moving very, very slowly, they tend to be more affected by your intermolecular forces of attraction. Okay, so I like to use this scenario. Imagine two scenarios. Number one of your classmates runs very quickly towards a door and bangs into it. Okay, I know this is very sadistic, but if it helps you to remember, that is good. Right. In the second scenario, the same friend runs towards the door, but this time you try to stop it by pulling on to his shirt. So what happens in the second scenario is this, that your friend will bang into the door with a lesser amount of force. So what happens when your intermolecular forces become significant is that the particles will hit the walls of the container with lesser force, and therefore the pressure exerted or the pressure measured will become lesser than what is expected if there were no forces of attraction at all. Meaning your pressure measured or your pressure actual is actually less than that of an ideal scenario. The second condition is that of high pressures. High pressures are usually associated with very small volumes of the container. Okay, when you have a very small volume, now the volume of your particle or your size of your particles becomes significant, right? The example that I always give is this. Imagine I have sesame seeds and almonds. If I throw them into a swimming pool, all right, it's not going to cause a big difference in the volume occupied. However, if I put them into a small bun, all right, if I put a lot of sesame seed plus an equal number of almonds into a small bun, the bun containing the almonds will appear to be slightly larger than that of the sesame seed. Okay, so the actual volume or the volume that's measured will actually be slightly larger than that of an ideal case. Now we can represent the deviation from ideality in the form of a graph. So the graph will look something like this. Okay, we are going to plot PV over RT against pressure. Okay, so in the second video, remember we learned how to draw graphical plots. So if we look at starting from the ideal gas equation, PV equals to nRT, okay, and we rearrange until the y variable exists on the left, so PV over RT, you can see that it's actually equals to n. Okay, the x variable p doesn't appear on the right hand side, so the graph is a constant graph. Okay, and if we are looking at 1 mole, all right, if we are looking at 1 mole of a gas, this y value is actually 1. Okay, so when you plot PV over RT against P, you actually get a straight line that remains constant at 1. This is the case for an ideal gas. All right, now what happens? What happens when you have low temperatures? Remember, at low temperatures, the intermolecular forces become significant. All right, so the pressure, the actual pressure will become lesser than the ideal pressure. So your PV over RT, if P becomes smaller, okay, that means your PV over RT now will become less than 1. So it will appear below 1 at low temperatures. Okay, what happens at high pressures? At high pressures, your volume becomes significant. The volume of the particles becomes significant. Therefore, the actual volume occupied by the gas will be larger than that of the ideal situation. So your PV over RT will become more than 1. Okay, so you'll be above 1 at high pressures. So for a non-ideal gas, if you plot PV over RT against P, this is what you will generally see. Okay, so this is an example of a plot that you may get for a real gas or for a non-ideal gas when you plot PV over RT against P. Okay, for non-gases that behave non-ideally, we sometimes call them real gases. So there are generally 2 types of questions that you may get. The first type is where you are given the plots for 2 different gases, 2 or more different gases, and you're supposed to identify which plot belongs to which gas. Okay, so for example, over here, you have plots for 2 gases, methane and hydrogen gas. So you need to recall that deviation from ideality arises from a few things. From one, the intermolecular forces becoming stronger, more significant, and the volume or the size of the particle becomes significant. All right, so the general approach is this: the stronger the intermolecular forces, okay, the greater will be the deviation from ideality. Okay, or the larger the size, the greater will be the deviation from ideality on 2 bases. Number 1, the greater the size, in general you have stronger dispersion forces. Also, it occupies a greater volume. All right, so in this case, when we compare methane and hydrogen, it should be obvious that methane is going to give a curve that will deviate more from ideality, and hydrogen is the one that will give a curve that is closer to that of an ideal gas. So the next type of graph is where you are given the same gas but at different temperatures. So the key thing is to recognize that at high temperatures, the particles have more kinetic energy, therefore the intermolecular forces become less significant and the gas will behave more ideally. So in this case, for example, there is a green curve and a blue curve. The green curve deviates less from ideality, so it must be at a higher temperature than the blue curve. So in this question, we are looking at the plots of PV against P for gas X and gas Y. And given the plots, we are supposed to identify the gases as well as the conditions for the gases. So first, we are looking at PV against P. So we start from the ideal gas equation. This is your y-axis. Your x variable is nowhere to be found. So actually, the graph for an ideal gas should look like this again, PV against P. However, what we see in the question means that they are behaving non-ideally. So I think the first thing that we can spot is that gas X behaves less ideally than gas Y. Okay, why? Because it deviates more from a straight line than gas Y. So in this case, if we look at the two gases, we have sulfur dioxide and hydrogen. Okay, if you consider the intermolecular forces, if you consider the size of your gas particle, it is not difficult to identify that therefore SO2 must be gas X and H2 must be gas Y. Okay, so that will allow us to eliminate A and B. Next, how do we know whether C or D is the correct answer? Is this, that you notice that the initial Y value is different. Okay, and given that PV equals to nRT, gas Y, the initial Y value of gas Y is 2 times that of gas X. That means that the number of moles, okay, the number of moles of gas Y must be 2 times that of the number of moles of gas X. So if you compare the number of moles, that would tell us that the correct answer is C.